So, energy is the ability to do work. There are many types of energy: mechanical, electrical, chemical, nuclear, sound, light, and heat. And we'll talk a little bit more about each of those next week. But these are the types of energy, and the one that we're focusing on in this unit is different types of mechanical energy. And so we'll take a look at those. The three types of mechanical energy that we'll be looking at here are gravitational potential energy, which is what happens due to the energy that you get from the height of an object. Kinetic energy is coming from the speed of the object, and elastic energy comes for how something is stretched or compressed. Here it says a spring. It can be a spring, it can be elastic, anything that has that type of characteristic in the material. All energy is measured in joules, and so it's just like we used for work. And if you look back at the definition of energy, energy is the ability to do work. So you use energy to do work, or you do work to add energy. So gravitational potential energy is due to how high something off the ground is. How much mass it has, it also plays a part in it, and how much gravity, due to being on Earth, plays a part of that. So the gravity, as long as we're on Earth, won't change. But depending on the mass and depending on the height that you're holding it, is how it'll work together. In this next part, I'll show you with my son on how that works. So we have a 2-pound weight
and a 10-pound.
10-pound weight. And if with potential energy, the more mass, the more potential energy. Also, the higher you hold it. So if you hold it down here, hold it down there, and drop it, it'll hurt. That'll hurt more than this one. If you hold it up here and drop it, it'll hurt more and more and more. If you hold it up here,
I can't get it up there.
And drop it,
it hurts so much.
So much. So the masses and the height and gravity, but we're on Earth, so we're just going to keep that. Right?
Yeah.
Okay. Set them down. So when they're being held at the same height, the small mass will have less gravitational potential energy because it has less mass. So if you were to drop it on your foot, it would hurt less compared to a larger mass that has more gravitational potential energy because it has a larger mass there when they're held at the same height. If you keep the mass constant but change the height, the higher up you go, the more gravitational potential energy you have. So if it were to fall on your toe from a higher height, it would hurt a lot more than if it were to fall on your toe from a lower height. So when the mass is constant, more height gives you more gravitational potential energy. Energy is the ability to do work. There's three types that we'll be looking at. One of them is called the gravitational potential energy. And this energy is when something is above a lower point. So if you lift a box, let's say you have your box here, and you lift it up from here and you push it up there to some height, you're adding energy into the system. And in doing that, to figure out how much energy you have, you will take the mass that's measured in kilograms times gravity on the planet. So since most that we'll be doing will be calculated on Earth, we'll always say 9.81 meters per second squared times the height it is lifted, and that's in meters. So when you lift it up, we won't call it a distance, we'll call it a height because it is implying that it is above the ground. This is our potential energy. The biggest thing to know is that it is energy. That's why it's listed as an E. And then we have potential energy. And that's where the P comes in, energy. And energy is always going to be measured in joules. So when we say that energy is the ability to do work, work is measured in joules, and energy is also measured in joules. If we take and do a calculation here, let's say we have this let's say this box above here, let's say that the mass is 12 kilograms, let's say that we lifted it to a height of 1.2 meters, and we know that gravity on Earth is 9.81 meters per second squared if we're calculating the potential energy, and we have mass times gravity times height. And if we put in our numbers here, we have
12 kilograms times 9.81 meters per second squared times 1.2 meters. And when you calculate all of those, you have your potential energy is equal to 141.3 joules. So when we're talking about potential energy, talking about gravitational potential energy, frequently we'll just call that potential energy. When we're talking about that, it's because something is lifted up. When something's lifted up, it has a mass, it has gravity affecting it, and then the height. And those three things equally affect the potential energy that you have. Anytime you're rearranging one of the equations for potential energy, if you're trying to solve, you have potential energy equals mass times gravity times height. And if you're trying to solve for something over here, you'll cover up what you're solving for and divide by the other two. So if I'm trying to solve for height, I would cover up the h. I have m and g here, so I would divide out mass and gravity on both sides. Cancels out there, and I'd be left with height is equal to the potential energy divided by the mass and gravity. When you put it into a calculation, you need to make sure that you keep parentheses around it when you calculate it in the calculator, so it follows order of operations. If I want to solve for mass, I would cover up mass and then divide by g and h. So g and h, g and h, those cancel out, so I would have mass equals potential energy divided by g and h. Again, I would make sure that those are in parentheses if I calculated them. And if I had to solve for gravity, if you happen to be on another planet, you're still using mass times gravity times height. If you cover up the g, you're left with m and h, so you would divide by m and h. M's cancel out, h's cancel out, and you'd be left with g equals potential energy over m and h. I don't know why I got that there. Potential. Either way, in all three of these rearrangements, you start with the potential energy and divide by the other two, every time being sure to calculate them in parentheses on your calculator.
Both the truck and Micah are not moving very fast here, but they're moving at the same speed. This truck is a little smaller, but it's moving quickly. And so when these two are moving at the same speed, Micah has more mass, so he has more kinetic energy. And this one moving quickly has, compared to the slower truck, has a higher amount of kinetic energy because it's moving quickly. The masses are pretty similar.
Kinetic energy is energy in motion. So when something is moving, it can have kinetic energy. The equation that we have for kinetic energy looks like this. We have E for energy. K tells us it's kinetic energy equals 1/2 mv squared. In this situation, m is the mass measured in kilograms, and v is the velocity of the moving object measured in meters per second. You'll take that value and you'll square it in the equation. Again, our E stands for energy, so and K is kinetic. Kinetic energy is what this shows up as, and again, as any energy, we're measuring in joules. So if you were to have a situation where you needed to solve for your kinetic energy, you would have your kinetic energy equals, let's say we have a mass of 750 kilograms, velocity of 22 meters per second, and we're looking for our kinetic energy. So you'd say kinetic energy is 1/2 mv squared. So you take 1/2 times 750 kilograms times 22 meters per second, and you'll square that whole value. And when you calculate that out, you would end up with 181,500 joules. So it's a pretty big number when you're talking about the kinetic energy that's going on here. If you're in a situation where you need to rearrange for either mass or velocity, you would start with kinetic energy equals 1/2 mv squared. To bring the half over to the other side, you would multiply by 2. And so 1/2 times 2 gives you 1. So you'd have 2 kinetic energy equals mv squared. And if I wanted to solve for mass, I would just divide by v squared. So I'd be left with mass equals 2 times my kinetic energy divided by v squared. If I wanted to solve for the velocity, I would start off with ek equals 1/2 mv squared. Again, I'd multiply both sides by 2. Multiplying both sides by 2, I have a half times 2. Half times 2 gives you 1, so I have 2 ek equals mv squared. I want to get v by itself, and so I'll divide by m, and that gives me that v squared is equal to 2 times my kinetic energy over my mass. But I can't do anything about that yet. I have to take the square root of both sides. And I would have v is equal to the square root of 2 kinetic energy over mass. That's what that would end as. Up here I switched the k and the e, ek. That's what we're looking for.
So the farther back you pull the stretchy part here, the more energy you're adding into the system. So farther, farther, farthest, you get more energy in what you're doing. And if you were to change from having a stretchy thing like this and using a different type of rubber band that might not stretch as much, then you'd have less energy, or a tighter rubber band, you'd have more energy.
The third type of energy that we'll talk about is elastic potential energy. We'll frequently talk about this as elastic energy. And this is energy from something being stretched or compressed. So if you pull a rubber band apart, or if you push a spring, you have energy that is ready to go there. This is measured by, we have EE for elastic energy, is equal to 1/2 kd squared. EE is our elastic energy, and that's measured in joules. K we'll talk about in a moment. D is the distance the spring is compressed or stretched. And it has to be measured in meters. It doesn't matter if it is compressed or stretched. So if it's pulled apart or pushed together, the distance in either direction will give you the same amount of energy. K is something called a spring constant. And that's a measure of how difficult it is to stretch that spring. If it has a low spring constant, I can easily pull it apart. And when I let it go, it goes back into its form. If it has a high spring constant, it'll be more difficult to pull apart, but it'll mean it will have more energy. We measure that in newtons per meter, is what that will show up as. So you might see a problem like this, where you have a spring constant that has a K of 45 newtons per meter. That means it will take 45 newtons to stretch that spring 1 meter if you can stretch it that far. You can do, it breaks down by centimeter, even smaller if needed, but that's what the measurement shows up as. And let's say that we're going to stretch it for 20 centimeters. But remember that your measurement has to be measured in meters, so you would move that, you'd convert that into 0.20 meters. And if you wanted to find the elastic energy, you would use EE equals 1/2 kd squared. So you'd say 1/2 times 45 newtons per meter times 0.20 squared. When you do that, you would end up with 0.9 joules of energy for your elastic energy. If you need to rearrange this, it's similar to what you would do for kinetic energy. Here you have EE equals 1/2 kd squared, and if you needed to solve for K, you'd start off by multiplying both sides by 2. 2 EE equals kd squared, because the half and the 2 cancel out. And then you would divide by d squared, giving you that K is equal to 2 times your elastic energy over d squared. If you needed to solve for the d, you would start off with elastic energy equals 1/2 kd squared. You would multiply both sides by 2. The half cancels out. You'd have 2 EE equals kd squared. Divide both sides by k, And you still have that 2 over k equals d squared. To get rid of the square, you would take the reverse of that, so you'd square root both sides, leaving you with the equation that d equals the square root of 2 times your elastic energy over k.